Alright class, so the first thing that you have up on top is a review from grouping from yesterday. Remember to group, you take the GCF out of the first two pieces. So x squared comes out of the first two pieces and you're left with an x plus 3. And then you take a GCF out of the last two pieces. And then what you do is you take one of the parentheses pieces as long as they match, and that's one of your factors. And then you take the outside pieces and that forms your other factor. And that's it. So we have x plus 3 and x squared plus 10. Okay, so we're going to do some weird 3 by 1 and 1 by 3 factoring today. It's a little bit different. When factoring these, there will always be a perfect square trinomial . It would help if I could spell that. And then you have to check for difference of squares. So let's look at this first one. You have to identify which three pieces you can factor into a perfect, or that is a perfect square trinomial, so you can factor it into a square of a binomial. And that's kind of like when we completed this square. So if you look at these three pieces, you can factor that into an x plus 3 quantity squared, and then you have the end piece still attached. And then if you look at this, there's something being squared here. This piece is being squared, and we can also say that 7y is being squared. So that means the a part of my difference of squares pattern is x plus 3, and my b part is 7y. So now I can use the difference of squares pattern. Remember, that's the one with the conjugates. So we have x plus 3 plus 7y. Nope, I don't need two of those. And then x plus 3 minus 7y. And then double check to see if you need to distribute negatives. You don't, so the final answer is x plus 3 plus 7y and x plus 3 minus 7y. Okay, so the next one is similar, except for we have an x squared here, and then we have a y squared y in number. So actually this is going to be a 1 by 3. But you can't factor this yet because there's no two numbers that are the same that multiplied up negative 36. So we need to factor out the negative first. So if I factor out the negative, that becomes a negative and this becomes a positive, and then this becomes factorable. Y minus 6 quantity squared. Now we're going to use our difference of squares pattern because we have a minus sign here and two things that are being squared. A is equal to the square root of the first piece, which is 3x. B is equal to the square root of the second piece, which is y minus 6. And now I'm going to put that into my a minus b, a plus b pattern. And then distribute the negative sign if it's necessary. And sure enough, we have negative y plus 6, and then 3x plus y minus 6. And that's the final answer. Okay, let's do two more of these, and then we'll do solving. This one's a little trickier, but if you look carefully, this one has a z in it, and there's the minus sign. This one has x's and y's in it, but you can see that you can take the square root of the first piece and get 2x, and the second piece is a 3y, but because the middle piece is negative, this should be a minus 3y squared. So that's how that one factors. Minus 81z to the fourth. And now we can do our pattern because again there's a minus sign here, so we have difference of squares. So a is equal to 2x minus 3y, and b is equal to, if you take the square root of that, 9z squared. Now I'm going to write out my pattern. So you get 2x minus 3y plus 9z squared, and then 2x minus 3y minus 9z squared. And then because the piece with the plus is in front, you can pretty much just take down the parentheses. There we go. Excuse me. So the last one we have is here. A squared stays. This can factor into b squared minus 25. Now if you notice, this is not a difference of two squares because we have a plus sign, so we can't use that pattern. Oh, and I forgot to square this piece here. That whole thing's squared. So you can't do the pattern we did for the other three here. The only thing you really could do is you can factor this if you want. So you probably won't see one of these. This is just to show you that sometimes you can't factor a 3 by 1 or a 1 by 3 unless you have a difference of squares. So I'm going to just stop that one there. And then you can't do anything with that one. So, alright, let's look at the next page. So factoring over the set of complex numbers. Basically, whenever you guys factor, we stop if we don't get nice numbers to split it with. For example, x squared minus 3. Okay, that's not a difference of squares, so we stop there. However, with factoring over complex, you want to get it so that each piece is an x and it's a 0. It's like an answer. Okay, so the first thing is we factor like normal. This one looks like grouping. And sure enough it is. I get x squared plus 25 and x minus 3. Now normally we would stop there because this is not a difference of two squares. It doesn't factor nicely. However, because it's complex, we are going to factor it. And here's how you factor these. It's basically solving. Set it equal to 0 and figure out what the answers were or are supposed to be. So when you take the square root of negative 25, you get plus or minus 5i, which are imaginary. But when we factor over complex, we want that piece. So what happens is over complex, this turns into x minus 5i and x plus 5i, and then x minus 3. Again, the nice thing about factoring over complex is that you can clearly see all your solutions. The solutions for this are positive 3, negative 5i, and positive 5i. It's always the opposite. And that's that. Number 6 is one of those ones where it's like factoring the old way, except for there's an x to the 4th. So the only thing that's different is these are both x squareds instead. Okay, so you need two numbers that multiply to negative 63 that add to 2. That would be positive 9 and negative 7. Alright, so let's think about what these would be if we solve them. You get plus or minus 3i, so that would break down into that. The other thing is positive 7 over here, so when you take the square root, you get plus or minus root 7. So normally we wouldn't want those in our factored form, but again, since it's complex, we will. So our final answer looks like x plus root 7, x minus root 7, x plus 3i, and x minus 3i. And again, by factoring in the complex, you can see all the solutions. Okay, so the last thing we're going to do is factor and solve. Okay, find every answer. Basically find the root, 0, they're all the same thing. X-intercept. Whenever you graph these, you're finding the x-intercepts. So, first thing you should do though is move everything over. Because you want it equal to 0. Second step, can you GCF the whole thing? No. Third step, figure out which pattern you can use. It looks like it would be grouping. So we take out an x squared and a 7. And now at this stage, we solve. We set it equal and solve. So we get x plus 4 equals 0. So x equals negative 4. X squared equals negative 7. X equals plus or minus I root 7. Now, I'm going to box this right now, but before we move on, you have to be careful. It says find all real roots. Real roots for this section. So this is a real root. These are not real roots. So I actually do not want those answers. Okay, so be careful on the quiz and test when you're reading that. Give me the real roots only for this section. As we move on down, you'll see that we will ask for the complex roots. First thing here, you GCF it. I can pull a 2 and an x out of everything. So I'm left with 3x squared minus 14x plus 3. And I already made a mistake. That 14 should turn into a 7. Okay. Set this piece equal to 0. You get x equals 0. You can try to factor this, but this doesn't. Two numbers that multiply to 9 that add to -7 does not exist. So you can't factor it. So you have to use quadratic formula. Okay. So I get x is equal to opposite b plus or minus the square root. B squared is 49 minus 4 times 3 times 3 all over 2 times a, which is 3. So when I simplify this, I get x is equal to 7 plus or minus, what's 49 minus 36 is root 13 all over 6. And then you look and see, can I simplify this? I can't break down to root 13, and then because of that you can't divide, so that is our final two answers. Double check, are these real answers? Yes, they are. They're not nice, but they are real. There's no I there, so these are our three solutions. Okay, solving over complex. These are the ones that trick people the most. If you see a cube, you can't just assume you take the cube root or that the answer is just 4. You have to move it, get it equal to 0, and then use your factoring of difference or sum of cubes pattern to solve that. So in this case, a is equal to x and b is equal to 4. So I'm going to do my cube pattern, which states that a minus b, so x minus 4, a squared plus a times b plus b squared. So now I can set both pieces equal to 0, and you do still get the x equals 4. However, I want the imaginary pieces too, and remember what I always said about these. When you factor, this is not factorable, so again we're going to do quadratic formula. You could also on this one use completing the square if you wanted to. X equals opposite b plus or minus the square root b squared minus 4 times 1 times 16 all over 2 times 1. So this turns into -4 plus or minus root -48 all over 2. Break this down, you get 16 and 3, so you get a pair of 4s. So we get it's equal to -4 plus or minus. There's a 4 that comes out, and since there's a negative under there, the I comes out as well. We're left with the root 3 all over 2. Now we can cancel. Remember, you can't just divide if there's one number that can divide. These both have to be divisible by 2. So we're going to say that my final answer, I shouldn't do that, is equal to -2 plus or minus 2i root 3. That's my final answer. Okay. And so is the x equal 4. And even though those are imaginary, that's okay, because again, we're solving over the set of complex numbers. So complex means give me all the solutions. Okay. Last one. Again, let's get everything over. All right. Next, you should try a GCF the whole thing. No x's come out, but I believe a 3 comes out. Sorry, I had to pause for a second. 18x squared plus 4x squared minus 72, I believe. Yes. All right. So we get that. Now this looks like grouping. I know some of you guys might be wondering, why are these 2x squared split apart like this? Well, that's because we gave it to you like this so you can group it. So we have 3. You can take an x squared out of here, so you get x squared minus 18 plus 4, and you can take an x squared, or you can only take a 4 out. So the factored form of this is x squared plus 4 and x squared minus 18 equals 0. And now we can set each piece equal to 0. So you get x is equal to plus or minus 2i. And if you set this piece equal to 0, you get x squared is equal to 18. X is equal to plus or minus root 18, which breaks down into plus or minus 3 root 2. Alright, good. So that is how you solve over complex. You can take anything, real and imaginary. When you solve over real, make sure you cross out your imaginary solutions.